Okay, so let's review. We are talking about volumes. Volumes in terms of the areas of the cross sections. That's a fairly simple idea. So once again, looking at the cross sections in some particular way, and that particular way is planes. The cutting planes are parallel to, perpendicular to the x-axis. Okay, so you can see it here. The simplest example is one of the cylinder. Okay, so we're cutting with the planes perpendicular to the x-axis, which produces a bunch of circles, so the area does not vary from one to the next, and as a result, integration is very simple. It is a constant. Okay. The next one was more challenging with the sphere. The size of the circle, which is the cross section, varies from 0 to r, and then back to 0. And so then the integration was slightly more challenging, as you can see. And we actually needed the Pythagorean theorem to figure out what that area is, the radius, what the radius of that circle was, and then the area. Okay, so that's the plan. That is the challenge is the same every time, which is that the description is verbal. Okay, it's just like almost a word problem. The description is of the geometric figure of the solid is verbal, meaning in this particular case it's a sphere, and you got to know what the sphere is. It's all points equal with a distance r from the origin. Okay, and then you look at and then we certainly not look at the sphere, but rather at what's inside the sphere. You can think of it as a cannonball, and then from that, from this geometry, so from words to picture geometry, and through some geometric facts such as the Pythagorean theorem, you finally getting to the to algebra. So because you cannot do calculus without algebra, really. If you want specific computations, they have to be accompanied by formulas. So the formulas are what's being integrated. Okay, so you have to figure out what that formula was, and we did. Okay, radius, then area, then we substitute area into our formula, and that's it. Okay, and then we got the area of the volume of the solid bounded by a sphere, radius r. Okay, so that works out the same way. I just want to point out a couple of things. Well, first of all, generally speaking, the cross section not only doesn't have to be a circle; it doesn't have to be anything specific. So you could have the solid could be, what about it is, you know what this is called? The technical term is the torus. Okay, and then imagine that if my x-axis is here, and I start crossing it with a plane perpendicular to the x-axis. You see what's happening? What kind of cross section it's going to have? Well, in the very beginning, what is it? It starts the same way. At some point that it will touch the surface. The plane will touch the surface, so there will be only one point. The whole cross section is a point, and then what's happening? What kind of cross section is that? Well, imagine you can think literally. I don't have a pretzel with me, but you can imagine you just cut a piece of it. What do you get? Then look at it. So the crust is say brown, and the what's inside is yellow. Okay, so what's the shape of the yellow, the piece of the what you see? What would it look like? Yeah, I suppose it doesn't have this exactly circle, but something circular, maybe an elliptic, because it's not exactly a sphere. So we're not expecting anything specifically nicely looking, but it's something like this, right? So the cross section might look like this. So something circular, maybe elongated. But as we proceed on, what's going to happen to it? We keep going, and the circle will be growing, or that something circular will be growing, and then what's going to happen?
It's going to split into two circles.
It will split into two, right around this spot over here. It will become first this way, like figure 8, and then it becomes totally two pieces. The cross section will have two pieces, and then it merges back again like this. Okay, and then becomes some kind of circle, and then ends with a point again. Okay, so that is totally possible that it doesn't have to be made of one piece. The theorem applies. The theorem that the volume as the integral of the area still applies. So it doesn't matter if we can compute those areas. We can carry out the computation of the volume. Okay. To illustrate the Riemann sum, let me show you the Riemann sum. I have it somewhere. Oh, here it is. A little more elaborate thing where the Riemann sums come from. So imagine we have the solid looking some weird shape, and then as you can see, what I did here, how I introduced the one-dimensional situation into this three-dimensional situation. I add the x-axis, and I do the partition of the x-axis with those x0, x1, x2, xn. Okay, those are the planes that cut through my solid. Okay, I'm cutting through my solid. The intersections are, the cross sections are those red shapes. They don't have to be circles or ellipses or anything. It's totally abstract. And then finally, what do I do? What do I approximate the solid with? I approximate with those shapes on the right. So to those areas that I have on the cross sections. They're giving me only the areas. In order to approximate the volume, the whole volume, I need a bunch of volumes of what? Of those little things over there. They look like, on the left, they look a little bit like maybe discs, okay, even though they may be misshaped discs, but they have a same width as we have talked about early on. And then, so once delta x is kind of longer, they will look more like cylinders. But it doesn't matter. The area, the rules that we started with is the same. So why does that right-hand side is actually manageable in comparison to what we have all the way on the right, the blue one? Why is it manageable in comparison to what we have on the left? That shape. That is early on our discussion was of volumes. Here it is. The volume of any kind of a cylindrical construction, a shape shifted vertically will be simply the height times the area of the two-dimensional region. Okay, so that's why we can handle it with no problem. We produce what's on the right, then it ends up to be a Riemann sum. It is a Riemann sum, so those delta x's multiplied by the areas of the cross sections give me the Riemann sum. I take the limit, delta x's go to 0, and we end up with a Riemann integral, which is what we carried out last time. Okay, so carried out last time is what I was talking about is this. Okay, so one more example of this, just for practice, and that is the, I'm going to do the cylinder, I'm sorry, pyramid. Pyramid. Okay, so I'm picking a right pyramid, meaning that it has a square base, and the side of the base is the same as the height, just to keep it simple. So in other words, let me just right away start to put it on the side so that we wouldn't have to worry about that. Okay, so that's what I mean by pyramid. So it's very much like those Egyptian pyramids. Okay, so they all have square base. The angle, however, I do not recall what the angle was, but it's pretty steep. Probably it's comparable. So what I'm talking about being, so if this side is, say, this side is, say, H. This side is H, and that is H, and that so the base is square H by H, okay, and then the height. The height is literally the height from the top to the bottom. So that height is in the middle of the. It is kind of invisible, but it's here. So from the base to the tip of the pyramid is called the height, and we will just for simplicity we'll choose it to be the same number. Okay, so so as you can see, so once again, if it looks like this, if this is my base of my pyramid, then this will be the height. So it's kind of proportional, nice proportion, I think, and it's not too different from the pyramids of Giza, I think. Well, anyway, so so I'm locating. Then I will put the x-axis along that height. So that height that is invisible inside the pyramid is where I put my x-axis. So it will be going on like this. So this will be the x-axis. But I don't really want to do a three-dimensional picture anymore. I'll follow the same idea as last time. I put everything on the sides, like this picture. So I put my my x, y, z axes in such a way that the x-axis goes to my right, and the y-axis goes into my eye. Okay, so the z-axis is vertical. So that this one is z-axis right here. Okay, so I want the same. So that will reveal the geometry to me, the geometry of the of cross sections. Okay, so let's do it. So this is what I'm going to have. So I'm taking my so what is going to look like if I'm looking at the pyramid from its side? Well, what does it look like? Well, if I'm looking at the sphere from the side and ignore the third dimension, I'm looking at a circle. Okay, so I'm trying to do the same. So imagine a picture of a pyramid, a photograph of a pyramid. What does it look like? Triangle. It's a triangle, right? So I do want to align a triangle so that I will be seeing exactly one side. So my eye is literally here. Okay, so a little bit back, so I'm standing there looking at the pyramid, and I'm not seeing. So if I have two more sides, I'm not seeing these two sides. That's what I want to do once again for simplicity's sake. So this is my x-axis, and I'm seeing a triangle. It's not exactly to proportion, but you can see. So this is H, and this is H, and this is H. Okay. So the height is H, the one that's inside the pyramid. No, these are H over 2, right? So the side is actually, whoops. What happened to H? Okay. So H is the height. So that's the extension of the pyramid along the x-axis, which is goes through it. So this is my z-axis. Y-axis once again pointing it at me. Okay, so, and this is H over 2, and this is H over 2. Okay, so, all right, so once you have this, you can actually try to look at the intersection. So if it is a pyramid, if it was standing like this, I would take it, that's how pyramids would probably be built, right? It's built layer by layer, right? And so what I'm doing is, well, certainly they knew how much stone they spent building it, but hypothetically, if you don't, then you just record the area of each of the, well, once you finish a layer, you record how large it is, and then just multiply by the number of layers, right? And it will give you the volume, the number of stone that you have used. Okay, so that's the same idea. So I will be cutting it like this, except now pyramid is on the side. So just because we the only reason is that we like the x-axis to be pointing to our right. Otherwise, it doesn't matter. So this is my cross section. Well, let me try it. Okay, so like this. So this is my cross section. It is at x. Okay. This is the area that, well, let me plot it here maybe, like this maybe. This is roughly what the cross section will look like. Okay. So once again, I set it to like a cutting off the top of the pyramid. And what is the cross section? What's the shape? What?
Square.
A square. Okay. Section is a square. Let's say, so unfortunately the size of the square depends on x. It's from large to small. At the top it is 0. So then it is say so what's its side then? Now we have to, what is its side? As it depends on x. Okay, so fortunately that is the size that I marked in red is in fact the size of our square. Okay, so that's very convenient because we start with a square, so we only need one dimension, and so the other side of the rectangle that we cannot see on the right has the same size, say same length. So all we need to figure out is this length of this cut. And that will give me the dimension. So say h of x. I have too many h's. S of x. S of x is the side of the square at x. Okay, so that's what we need to find. The geometry should tell us what it is. Okay, so if we just look carefully, let me blow it up. Once again, this is the x-axis. This is my x. Okay, so, or in fact, this is x. Maybe better way to put it. Okay, so this is h over 2. This is h. Okay, so I see why that doesn't matter. Anyway, okay, so the side of the pyramid, the height of the pyramid is h is visible. The base of the pyramid is also visible. This is h. Okay, the base of the pyramid. But we are not looking at the whole thing. We're looking only at one cross section, which is visible in red. And the length of the red one is what we care about. So okay, so what is it? Let me point out where it is. So this is S of x. Is this the side of our square? Okay, so what is it? Well, the idea is the same. So just like last time, there is no circle, but it works out still fine. This is the triangle, and from this triangle we should be able to figure out its sides, right? So let me erase this. Okay, so let me blow that up again. The triangle is the yellow triangle. Okay, so what is its bottom side? h minus x, okay, h minus x the bottom side. The height, what about the height? The left side. It's a bit trickier, but well, all we need to know is what this line is. What is this line? It is a straight line, right? So all we need is its slope and the y-intercept. What's the y-intercept? Or you can do proportions. It's up to you. Up to you. Let's do algebra. Let's do it with the equation of the line. So what's the equation of the line? So the y-intercept is h over 2, okay, and what is the slope? So at that point, forget about the red one, just look at the graph. Well, you can see it here, right? It passes through, this one is h, and this one is h over 2. So the slope is h over 2, h. What's the slope? It's is proportional slightly. H over 2, h, slope is well, rise over the run, remember that one? So rise over the run. What's the run? The run is h, and the rise? Almost. Negative h. So the rise is negative because we're going down, h over 2. So the slope is negative 1/2. Okay, so that's how you can catch all the geometry of the cross sections. They are given by this line of slope negative 1/2. That doesn't matter. You can achieve the same result with just proportional triangles, or rather similar triangles. Okay, and but it doesn't matter. At this point, all we need to find is so this is 90 degrees, so we're good, and so we're looking for the height based on, I guess this side didn't really matter. This is what matters. So this is hold on a second. This is x. This is x. This is x, and this is what we're after. This is what we're after, and we are more or less already know what it is. It will be that what we just found. We're getting only half, but that's pretty good enough, right? So the line is negative 1/2 x plus h over 2. Okay, where are we? We are at x. So the height of the elevation of the curve of that straight line above the x-axis will be simply, once again, negative 1/2 x plus h over 2. Okay, so that's this height. So then what's SOX? Twice that. Right, look at that red one, and we need the whole thing. We got only half of it. Above the x-axis, the other half below the x-axis, so multiply by 2, have negative 1/2 x x plus h over 2, multiplied by 2, I have negative x plus h, or h minus x, same thing. Okay, so that's my side. Okay, what's the next step? Once we know the side, what's the next step? The area. Okay, so the area of the rectangle, or of the square with the side, will be simply square root. So it will be h minus x squared. Okay, so well that does it. That's what we're going to integrate. So just take a moment to confirm. I suppose this once you have this, you confirm that it does make sense. For example, how the area changes. the whole thing starts at x equals 0, and the area is h squared. Okay, that's the base of the pyramid, h by h squared. Okay, and at the end, when x reaches h minus h is 0, so it ends with 0. So once again, from h squared to 0. Okay, so and you have your area, so it seems to make sense. And so we integrate. So the volume is integral from 0 to h. So along the height of the pyramid, and it is ax. So let me just go straight with this h minus x squared dx. Okay, so well, you could expand if you like. You could expand, but let's just say as an exercise, without expanding, how do we integrate this? Thoughts? Substitute, right? Substitution, so that we wouldn't have to do any algebra, but rather fairly direct. So u is equal to h minus x. H is a constant, remember? So so du is equal to negative dx. So our integral turns into integral, and this will be simply u squared. Right, this is u squared. Du is negative dx, so it will be negative du. Okay, and the limits are, these limits were with respect to x, and now we have new limits with respect to u. So x equals 0 turns into, limit for u, what is it? X equal to 0, u is h, and when x is h, u is 0, right? 0. Okay, so these are the limits, and I intentionally carried out the integration with substitution with including the limits. So it's a definite integral just as well. We don't have to go back to x. Or we could just as well deal with u. Incidentally, the meaning of u is also clear from the picture. It's if x is how far off the ground you are, and then u is simply how far how much you have left to get to the top. Okay, so it will be integral u squared du, so it will be u cubed over 3 from h to 0. Okay, so I plug in 0 first, so I'll have 0, and then I have h cubed over 3. The end. Okay. So as I understand it, the main challenge is still lies not here. Well, obviously, depending on how much experience you've had with integration, but still, most of the time, when you encounter a problem like that, integration probably will not be a major concern. It is to set it up correctly, and to set up correctly, it is the challenge is right here to sort out the geometry and figure out what the area is. So not the area, a number, but area function, depending on which way you put x. Incidentally, we could have solved this problem in a number of ways. Same cylinder. Same pyramid. For example, I could have put it upside down, and that way I wouldn't have to carry out this that substitution. I would have ended up with simply u squared. Okay, that's one way. Another way, I could have cut the pyramid. I could have cut the pyramid in vertically. How about so? It would be more challenging. So if my pyramid is standing like this, and along the x-axis like this, then my cuts would be more complex. So whenever description that you're facing is not specific enough of how you're supposed to do it, then you have to think about which way the cross sections are the simplest. So it was very simple once you hear the word pyramid to just keep the pyramid as you imagine it, and that's standing on its base. Okay, and so the x-axis would go along the that plane. Okay, but then look at what happens to the cross sections. So what are the cross sections? I'm cutting pyramid with the vertical cuts. What? I tried to make a picture here. It's not ideal here, but you try to imagine.
Would be like a rhombus?
Not a rhombus, but it will be quadrilateral, right? So that plane will cut the surface of the pyramid in will produce four edges. The bottom of the base, the top of that sloped of the slope, and two slopes on the side. So it's what? Trapezoid. A trapezoid. So the cross section looks like this. Okay, so the trapezoid is not really hard to figure out what it is, but notice that so you could do it this way. It would be slightly more complex, so rather than dealing with squares, you're dealing with trapezoids, and then the also extra challenge is once you pass through the center, through the top. At the top, by the way, it's going to become a triangle. The very middle cross section will be triangular, and then it turns into a smaller and smaller trapezoids again. So it's slightly more complex. But sometimes it works out just fine. So if you let me quickly go over what we have done, starting with the cylinder. Imagine, okay, so if I'm cutting the cylinder the way it stands on the left, not the way I put it on the side on the right. What are the cross sections?
They would be rectangles.
They will be rectangles. So it touches it, becomes a straight line, or just a segment, and then it pushes in. They become rectangles. Rectangles grow all the way in the middle, and then start to decline. Okay, so also it can be done definitely. Then in that sense, you won't have to do a lot of the complexity will be then hidden elsewhere. In integration. So your rectangle, your cross sections are simpler. They're rectangle, simpler than those circles. On the other hand, you're gonna the dependence of the size of the rectangle will be variable, unlike these circles that are constant. So the integration would be more complex. The result should certainly be the same. With a good thing about the sphere, I cut it this way, that way, or even this way. It doesn't matter. It will produce exactly the same shape. It will be circular. Okay, so well, that's the main lesson. One more time, the torus. If I start cutting the torus with horizontal planes. What's going to happen?
It would be like a circle minus a circle for the area.
Yeah. So in other words, it's a ring.
Right.
It's a ring. So circle minus cut out the circle in the middle. So when you touches it first, it produces a circle, and then it pushes in. The circle blows up or grows in thickness, and then keeps growing until it starts to decline and then disappears again. So just a matter of practice to produce this kind of function, and then once you do, then the algebra is, or the integration is typically fairly straightforward. Okay, so next is a longer topic. It is the topic about the density and mass, and even the center of mass. So this is, we certainly will rely a little bit on what we just have been doing, but generally we start with something way simpler. And to understand the meaning of density, we'll start with something simpler. Well, everybody knows what density is. You have an object. You have an object. So density is What's the density is if you have an object? How do you find its density?
It's the mass over the volume.
Mass over the volume. So as you can see, you already need, if you have some kind of figure, geometric figure, you need to know its volume in order to compute density. Okay. So, but it's not that simple. That only will give you the average density to begin with, and that's why that is the complexity, because density might change from location to location. So that's the challenge that we are facing, and so we start facing it when with something simpler than a solid, but rather going down to two-dimensional regions. So some flat piece of wood possibly also could have variable density, or a piece of metal made of an alloy. We say this is still too complicated. We go back to something very simple. So it is like a rod. So not a plate, not a solid, but a rod. So one-dimensional piece. And the challenge is, well, it might look like this. The challenge is that the density might vary. So as you can see, this is what I'm trying to suggest here, that one end is denser than the other. Okay, and that change might be gradual. Okay, so maybe you have two, you're creating an alloy and you forgot to, mix it up. Okay, so you have two metals, you put them together, two rods, like maybe put them next to each other, and they start to penetrate through each other, but not all the way. Okay, so the one metal is heavier than the other, so one end is still heavier than the other. So it's quite possible that the variability is entirely continuous. Okay, so so what do we do about it? Well, another example actually is maybe rather than a rod, maybe it is like a glass. Think of this as a glass, and you have a liquid in it, and it starts to settle. There is something maybe suspended in some I don't know, maybe cocktail or whatever, and something heavier than just water starts to settle down and is not fully settled down. And so once again, the top will be lighter with less density. It doesn't have to be a mass necessarily. We could discuss density of a particular material inside of a certain object or liquid. So we can totally ignore the water in that glass and concentrate on that particular material that is suspended in it. And it is very typical for that material, the density of that material to vary from top to bottom, and it increase as we going down. Okay, so initially maybe it was stirred, and then so it was equal to begin with, but then with gravity pulls it down gradually, and it becomes lighter at the top and heavier at the bottom. So that's another possibility why we care about it. And then it seems like the point, of course, is to make it one-dimensional so that we don't have to go too far from what we did in Calculus 1. And the idea is that the variability of the density only varies in one direction. Okay, so once again, it's either with that glass that you can say that on the horizontal level it has the same density. So there are many locations here, right? But we assume you can say probably justifiably that they have exactly the same density. So, but it does vary this way. So density varies. Density varies in the vertical direction, but not in the horizontal direction. So, which makes the whole thing one-dimensional. So how do we proceed? We just say the density is a function of one variable of x. So wherever I put my x-axis, it's my choice. I will put it along the line where the density varies. Okay, so the rest then I can ignore. I only care about the where it varies. So it could be, I don't know, y equal f of x once again. So it's literally the density as it varies from point to point might be increasing, decreasing, and any kind of function you can think of could justifiably model some kind of density. So this is the simplest one, like this. How about maybe like that? Okay, so light to the left, and this is say 2, this is 1, 1, 2. Okay, so once again, you have two materials, two maybe, and they're put together, and they're gradually penetrating through each other, and well, they did, but that the process is not as unfinished. So maybe once was like 1 pound per. Well, what I'm talking about probably definitely makes sense to mention. This is called the linear density. So in other words, we're not looking volume by volume, but rather looking at point by point on the x-axis. And once again, every direction away from the x-axis does not produce any variability. So we are looking at density over of such a material. And then the definition of density, even average density will be, rather than mass over volume, it will be mass over length. Okay, that's the definition. But once again, it is average density we're talking about here. What I'm trying to introduce, well, it's not really definition. What I'm trying to introduce here is a function that varies continuously. So what we have here, it is a single number for the whole thing, and that's why we call it average. We take the whole mass and we take the whole length. Okay, so for example, in this example on the left, let's see. Well, what's the average density of this object? So the density varies from 1 to 2 in a linear fashion. What's the average density? 1.5. Okay, so that just intuition tells you that there is nothing fancy going on. So that will be the average density between 1 and 2, and it varies in a linear fashion, so it will be 2. And now let's understand the 1.5 in terms of this formula. So 1.5, the length is 2, right? So 1.5 is equal to mass over length, with length equal to 2. So the mass is what? 3. Okay. So, all right, so the mass appears to be 3, even though we usually go the other way, right? You have mass and you have length or volume, and you divide, you get your average density. But this time we actually went the opposite direction. From a linearly changing, continuously changing density, we got to its mass, and turns out to be 3. What's the meaning of 3? Can you see 3 on this picture? Yes, yes, it is. The area under the graph, which happens to be a trapezoid, right? Once 1 by 2 and multiplied by the average of 1 plus 2 divided by multiplied by 2. Okay, by 2 multiplied by 2. Okay, so that's the trapezoid. The trapezoid, which the area of which is the average of the two bases multiplied by the height, which is what I have here, right? But we have been studying integration enough to know that we are really after this area. We better describe it as the area under the graph, which is long term is better. right? So because we know that now if next time we change this linear dependence, linear density to some density that's not linear, might be variable in an entirely unpredictable way, we know what to do. We know that the mass will be the area under the graph. Okay, so the area under the graph. Well, so let me try to put it here in words. So the mass is the area under the graph of the linear density. Okay? Which makes it what? So linear density is yf of x, so which makes the mass the area under the graph, the integral. So the Riemann integral of f. So you can actually write it out as mass equal to integral from a to b fx dx. Okay. One way, so that certainly is a starting point. If you have the density, then you integrate it and you get the mass. Okay, so if you go back to think about this for a moment, if we go back all the way back to an object that is entirely uniform, which means that the density is constant, and what does this integral turns into? So f is constant, then what? What does the integral turn into? How do you integrate a constant function? Or think about instead of having a trapezoid there, what kind of shape do we have? We have a rectangle. In the area of the rectangle, it's simply the base times the height, right? So it will be f times b minus a, right? So, and once again, if you think about what we're getting here is the mass is equal to density times the length. Okay, density when the density is constant. On the other hand, but that certainly is too simple for us at this point to deal with. So the density will be a variable every time. And so that is my integral. To take it one step further, however, let's utilize calculus 1 a little bit more. What if the top or upper limit is variable? So in other words, I'm looking at which gives me the mass, not of the whole rod, but rather of this piece from a to x. So this is the only thing that we're talking about. So this is my m, as it depends on x this time. So the mass of the rod from a to x. Okay, so m of x. Then what do we know about this function relative to f? The word I'm looking for is antiderivative, right? It's the, if you take a Riemann integral and make the upper limit variable, you end up with the antiderivative of the function. So that. Okay, so we'll just continue on next time.